Welcome back to Complex Differential Geometry. Today we're going to be doing orientations and integration on the manifold. So last time we were doing lecture 6, so this is lecture 7. And let's do a brief recap of what we did in lecture 6. First of all, we started talking about differential forms. So the way we went into differential forms is that we first started out in the tensor algebra, which came from the idea that what if we add up the tensors from the different tensor spaces in a formal sum? What kind of space would we get there? That's the tensor algebra. And from there, if we take the antisymmetric part only, if I can spell antisymmetric, so then the antisymmetric part of this algebra is called the exterior algebra. And specifically, we were interested in the exterior form algebra. So the exterior form algebra is the algebra of 0 k tensors, for k is between 0 and the dimension of our manifold. In general, it doesn't have to be restricted to the dimension of the manifold, but for the case of there being a manifold, we're going to restrict it to the dimension of the manifold. So the elements of these spaces are called exterior forms. Exterior forms. And from the exterior forms, so these are defined pointwise. So they're defined on each TP star M. Or let's say they're actually defined on T 0k of M, the tensor space, and we write the alternating projection of that as lambda k of M. So, or you could say lambda k of TP star M. That also works. So then we go to the bundle. So we go to the exterior form bundle. Exterior form bundle. This is lambda of T star M as opposed to TP star M, which is the direct sum of k less than k is equal to 0 to dimension of M lambda k TP star M, or lambda k T star M. There we go. So these are all the exterior k-forms. And so this is the exterior, sorry, this should be the exterior k bundle, right? And so, or the kth, I think it's called the kth exterior bundle, kth exterior bundle. And this is just the exterior bundle, or the exterior form bundle, if you want to be specific. And so if we take a smooth section off of this bundle, gamma of, nowadays I don't know if originally I used gamma as just the space of sections or the space of smooth sections, but nowadays I'm using it to mean smooth sections, so just as a point of reference. So this is by definition omega, sorry, so if we put a k there, so then this is omega k on M. These are the bona fide, well, real differential, or let's say the full thing, real exterior differential k-forms. So then once we have this, so these are 0k tensor fields, specifically antisymmetric 0k tensor fields. And once we have this, we can break these down into, we call this PQ decomposition. PQ decomposition. And so we can define this space omega PQ on M, which is by definition equal to omega P on M plus omega, or I think it's times omega Q on M forms. And we saw that on using these forms on an almost complex manifold, you get this exterior derivative, and it's an element. The exterior derivative of a PQ form alpha is an element of in the. So this is for an almost complex manifold. If we go to a complex manifold, then we find that D alpha is an element of just the first part, P plus 1 Q plus omega. I'm omitting that little m at the end as I do usually. So P Q plus 1. And that means that we can decompose D as partial plus partial bar, where these are called the Dolbeault operators. And they fulfill some nice conditions. Partial square is equal to 0. Partial par squared is equal to 0. And partial after partial bar plus partial bar after partial is equal to 0. So these are some powerful results that we are going to be able to use on complex manifolds. So the next thing to do after you define something called the Dolbeault operators is probably to talk about the Dolbeault cohomology group. But before we can do that, because we've just defined differential forms, it behooves us to talk about orientations and integration, because that's something we're going to need in the future. So today we're going to be talking about that, orientations and integration. So, well, let's just focus on the first part first, orientations. The reason we need orientations is because of integration, in fact. So let me motivate the main reason why we care about orientations right now. We want to integrate things on the manifold. If we don't define an orientation on the manifold, this integral is going to be inconsistent between coordinate systems. So let's say my integral, so we're going to primarily be trying to integrate these differential forms on the manifold. So let's say my integral is this, right? That's a differential form. Let's say that it's equal to plus k in a certain coordinate system. When we go to a different coordinate system, we don't want it to suddenly change to becoming minus k. And this could happen if the orientation of the coordinates changes. So if you go from a left-handed system to a right-handed system, then this could happen. So we want to avoid inconsistencies in our manifold. So like our manifold has an atlas, right? That's what makes it a manifold. So this atlas is needs to be consistent in a certain way. The charts on this atlas need to agree on this value of this integral, whether it's positive or negative. So in order to do that, we need to define the orientation of the basis. So that transformation matrix has a definite sign. This, you can think of that as the transition map. The transition map between coordinates. So that's why we care about orientations. So the next question is, how do we define a orientation? So we can define an orientation on a, so first we're going to start off with vector spaces. So vector spaces, we're then going to use that like orientations on vector spaces. So then we can orient a tangent space. And we're going to use a bottom-up approach here where we're going to orient each of the tangent spaces and then we're going to attach them together in a smooth way to, so like a smooth assignment which will give us an orientation on a manifold. Sorry, this is getting a little messy. Let me take this to this side. So orientation on the manifold. Right. So so the first things first. So let's define orientations. Orientations on real vector spaces. And then we're going to use the fact that a complex vector space is a twice-dimensional real vector space in order to extend this to the complex regime. So let's start with that. So the first thing is that in defining orientations on a real vector space is that one thing that I cut out of the last lecture for the sake of brevity and pacing is that there are these things called, so we talked about exterior forms or exterior K-forms, which are antisymmetric K 0K tensor fields, right? Tensor fields. But you can also define exterior K vectors. That's what Chern-Chen and Lam calls them. Exterior K vectors. These are antisymmetric K0 tensor fields. And we kind of need to understand them a little bit, I realized, in order to understand this idea of what how we're going to define an orientation. So there are these things. So these things are called multivectors. And they define something called a K volume. A one volume, or like an oriented K volume. So an oriented one volume is an oriented line. So something that looks like this, or a line segment, I guess. So this is an oriented one volume. So an oriented two volume is an oriented area. And so that looks kind of like this. All the arrows have to kind of point along the same direction. So then, one second. So then there's this overall orientation. In 3 dimensions, this is sometimes dualized as the normal vector, but we can't rely on the existence of a normal vector because we don't know if there's any space outside of the manifold. So instead of thinking about the normal vector, we think about this oriented area inside the space itself. So this is a 2 volume, and then similarly, I'm not going to write out everything again. There's a 3 volume. The way you construct this, it's a little interesting, or it's interesting. This you make sure that this one goes this way, then this one has to go in the opposite direction. And then same thing here, they all have to go against the grain. So that's how you define the oriented 3 volume, which is just an oriented volume, 3 volume. So a K-form, we didn't discuss this the first time we did lecture 1, but something that I amended onto lecture 1 after the fact is the idea that covectors are objects that measure vectors, and by extension, forms are objects that measure multivectors. So a K-form measures a K volume or a K vector. And the thing it measures is assigned n volume, or assigned k volume, right? So we don't really care about the magnitude of this assigned k volume. We care about the sign of the k volume. The sign is what gives us the orientation. So this is how we detect the orientation. We define this, we don't define this k vector. We could do it that way, that these are both dual descriptions. What we're going to do is we're going to define the k form that measures the k vector, and that's going to tell us the orientation. This is called the orientation form. Orientation form. When we're talking about the vector space, this is an exterior form. We're not talking about a differential form yet because we're on a single vector space. But so this is an exterior form, and it's either called the orientation form, or more commonly it's called the volume form, because it's a form that tells you how to measure volumes on a space. This is what we're going to call it. We're going to call it the volume form. So now we're ready to we are ready to define an orientation on a vector space. Definition, orientation on a real vector space. Yeah, it's called a top form, but top form is not the main thing. Like, there are many things that could be a top form. It happens to be a top form, but it's a specific kind of top form. Okay. So I was reading the comments there. So okay. So let V be an n-dimensional vector space. So a real vector space. Then volume form omega is an element of lambda n of V star, which is a non-zero top degree form. It's a choice of non-zero top degree form. There are many top degree forms. It's a non-zero choice of top degree form. So as we said, it assigns a volume to, so like a scalar, assigned scalar, to each oriented n is a long word, parallelepiped, which is a shape that looks like this. So kind of like you can think of it as a slanted cuboid. That's a parallelepiped. So it is unique up to a scalar factor. And that's going to be very important, the fact that it's unique up to a scalar factor. So that is an orientation on a real vector space. It's equivalent to, so this idea is equivalent to I made a mistake. This is not an orientation on a real vector space. This is a volume form. We haven't defined, oopsie, this is a volume form. And then we're going to define an orientation. Orientation. Okay, so given that this is, yeah, I said we're going to define an orientation and then I just started writing volume form. That's funny. So uh, an orientation on a real vector space, we're like almost there though. So let's say that we have a choice of volume form on uh, V star. So on real space V it's a choice of volume form on V star subject to an equivalence relation. Whenever you see this idea of something being unique up to something else, it always kind of boils down to an equivalence relation. So equivalence relation. Let's say that we have two volume forms, omega in the B basis, the curly B basis, is related to or equivalent to omega in the B prime basis if omega in the B basis is equal to the determinant of the transformation matrix. So T is a linear transformation that looks like this, V to V prime. It's the coordinate transformation uh, multiplied by omega in B prime. So if this is greater than 0, then they're equivalent. And so that equivalence relation, the equivalence, or like the equivalence class of such bases defines an orientation. So that's where we're saying that there's like the plus orientations and then there's the minus orientations, because that's really the only signs that this transformation can have. Right. Uh, if two orientations have the same sign, then they'll have the same or if two vector spaces have dual spaces with volume forms that have the same sign, then they'll have the same orientation. And if they have opposite signs, then they'll have opposite orientations. So then we have this sub-definition of the standard orientation. Standard orientation. So the standard orientation, we want to call it omega standard on the dual space, is just what we get if we apply the alternating map from last time d on the basis tensor dx1, dx2, tensor dot dot dot, tensor dx. What did we call the vector space? We called it n-dimensional. So n. Which just results in the wedge product. That's just the definition of the wedge product. dx2 wedge dot 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 wedge dxn. Sorry, I have to remember to speak up. Um, so right, and where this is the alternating map. Alternating map, which as we noted last time, is a map that takes the tensor product and projects out its alternating part, which ensures that this is in fact a K form or a top degree form. Okay, so the only way we can reverse the orientation is by having a transformation where det of t is less than 0. There's a case where det of t is equal to 0, but this is degenerate, and for any well-defined manifold, this will not exist. So we're not considering the case where det t equals to 0. If det t equals to 0, you have a coordinate system on your manifold that has less than n coordinates, and that is not consistent with all the definitions that we have had so far of the atlas. So this situation is not possible. So we're not going to worry about this. Okay, so we're going to look at an example of orientations. One of the most famous examples of orientations is the left-handed coordinate system versus the right-handed coordinate system. So let's say that if this is x, this is y, and this is z, then this is a right-handed coordinate system. Sorry, it's not right-hand side, right-handed coordinate system. And if this is x, this is z, x, z, y, that's called a left-handed coordinate system. And these have the opposite orientations. Opposite orientations. So for example, so on this one, the standard volume form would look like this: dx wedge dy wedge dz. And on this one, oh well, this one would not. This would be the standard orientation, and this one would not be the standard orientation. It would be dx wedge dz wedge dy, which is equal to. Remember that we have that anti-symmetry property of the wedge product. So if we were to flip these two, right, we would gain a minus sign. So then we get dx wedge minus dx wedge dy wedge dz. So these, so you can see that they have a minus sign between them. So these are opposite orientations. This is actually related to this idea of shuffling the basis vectors, and you can see it from this diagram that we showed here. The basis vectors here are 1, 0, 0, 0, 1, 0, and then 0, 0, 1, right? And for this one, it's 1, 0, 0, but then we have the z basis vector, so then 0, 0, 1, and then 0, 1, 0. And obviously there are other permutations of these basis vectors, but you can show that because there are only two signs that are possible, they're either equivalent to this one or they're equivalent to that one. So there ends up being two equivalence classes. So there's the equivalence class plus and the equivalence class minus. These are just labels. We could call them whatever we want. We could call them P and N if you wanted to, but there are two of them. There are two orientations. So these are orientations on R3. So that's an example of orientations. So the orientation on the dual space, orientation on the dual space, so this is quite simple. So we said that, okay, so if we have V, then the orientation is defined by omega on V star. Simply, the orientation on V star is also dependent on omega on V star. That's it. They have the same orientation by definition. Same orientation. This only works for the dual basis of on V star, right? If we have, let's say, EJ, J, EJ, then I don't think I'm supposed to put parentheses around that. Anyway, then its dual basis is epsilon k minus J star epsilon k. So these two will have the same orientation. That's the idea. Okay, moving on. Now for a big result. Big result theorem. Uh, so these kind of bases, every real basis induced by J on a complex manifold of a certain complex manifold is has the same orientation. So we're going to prove this. The proof of this is at once not too involved and also very complicated. The explanation is subtle, but the proof is not very long. So we already know. So let's say that we have two bases, right? We're going to call them for symmetry AJ, J, AJ, and BJ, J, BJ. So we can then form the dual bases, right? So I'll call that alpha k minus J star alpha k. Our job, by the way, is to show that these have the same orientation. So I mean, like, let's say that this is from one local chart, local coordinate, right? That's the constraint on what AJ and BJ have to be. So this is another local coordinate. Local coordinate. So here we're going to have a similar naming scheme. We're going to call this beta k minus J star beta k. And there's two interesting steps to this proof. Firstly, we're going to move from this basis to the eigenbasis of J. And this proof was the proof that was supposed to be in the lecture on complex structures, but we couldn't do it because we didn't know what an orientation was. So now that we know what an orientation is, now we can actually apply this proof. So I'm gonna like call back to this idea that we had that epsilon. So there was this lambda j or lambda k, let's call it. Lambda k is equal to epsilon k plus I epsilon m plus k, right? We're going to use this idea here. So we can show, or if we use pairs of our bases, then we can find that we have this minus J star of alpha k is equal to minus I over 2 lambda k. So this gets translated to, let's just replace this. This will become alpha. This will become alpha. And instead of calling it alpha m plus k, we're going to call it minus alpha minus J star alpha k. So this is going to be equal to, you can check it at home if you'd like, lambda bar k. So this is the eigenbasis. It looks like this, lambda k, lambda bar k, where j star of lambda k is equal to I lambda k. It's an eigenvector. That's what we're saying. So if we wedge all of them together, right there, if we're doing here, we have only one k being considered. If we wedge all of the k's together, then what do we get? So 1 less than k less than m, we get alpha k, wedge j star. I think this shouldn't be this. This should be j star alpha k. Yeah. So then we get big wedge 1 less than k less than m. So we're just wedging all of them together in a big line. So we'll get m copies of this, right? Because k is going to go from 1 to m. So we get, yeah, in fact, let's put that in front. Let's put that in front of here. Minus I over 2 to the power m, right? One for each pair like this that we are getting. So like one factor of this. So there are m of them. So we'll get this lambda k wedge lambda bar k, right? So now this is interesting because what it says is that, so this is one of the volume forms, and this is a different basis, and this is a different volume form. And there's this factor out in front, which because of a factor of m mod 4, right? Minus I, to the power 4 is equal to 1. So there are 4 different values that this can take: minus I, plus 1, minus 1. It can have 4 different values, right? So we're going from the real space into the complex space, and this is not necessarily positive. So there's some chance, or like it's possible for some values or for some bases that this will flip. So there's a flip here. So this is interesting. But remember, there's going to be a similar flip for both of them. By that I mean, I'm not going to write everything out, but just to give the idea, beta k wedge j star beta k is equal to minus I. It'll give you the same thing, minus I by 2 to the power m, 1 less than k less than m. Let's call this basis mu. So mu k, mu bar k. Notice that here this factor out in front is the same. So if the crucial point is that if this flips, then this flips, and if this one doesn't flip, then this one also doesn't flip. So there are 2 flips, and these 2 flips are going to cancel each other out. That's a big thing in this proof. So these 2 are going to cancel each other out. And the other thing is that if we compare these 2, if we were to go from this eigenbasis to this eigenbasis, what would happen? So there's definitely a non-degenerate matrix that looks like this. Lambda mu j is equal to lambda k dot matrix G kj, right? And so the forms here are going to be mu k wedge mu bar k is equal to k is less than m less than 1. I never know whether I want to commit to writing all of this. So lambda k wedge lambda bar k, but there is an extra factor of det g times det g bar. We get a det g because of these, and we get a dead G bar because of these. And what this means is, if you're already catching on to what's going to happen, is this is mod det G determinant of G whole squared, which is a positive number. So these two volume forms give the same orientation, same orientation, right? So now we have the full picture to construct everything. I'm going to write this in short because if I write it in long, it gets really unwieldy. The full diagram is going to be in the notes, but we'll call each of the bases by their first basis vector. So we have the AJ basis. This goes to the alpha k basis, or the alpha k dual basis, which goes then to the lambda k basis. This is the eigenbasis. And then we go to the mu k basis, which then we go back up to the beta k basis, and then we go back up to the bj basis. We wanted to know if these are the same orientation. But we can't compare them directly. So we're going along this chain of more complicated but more computable chain of orientation. So these are the same because of definition, right? So let me just say definitionally, these are the same. These are also the same because of definition. Uh, because the dual basis is defined to have the same orientation as the vector basis, and then these are the same, or these are not the same. These are either same or flipped, It depends on the value of m, but this is also same or flipped. And in a very special way, where if this is flipped, then that is flipped, and if this is the same, then that is the same. Overall, it's kind of like that thing that you learn: plus plus is equal to plus, minus minus is also equal to plus. So overall, we have no net change in the orientation because of these two. And here we also showed that these are the same because det G, the factor out in front is det G squared, right? So therefore, overall, AJ and BJ have to have the same orientation. And the only thing that we assumed about these was that they were induced. They were from AJ and BJ were local coordinates, and that these are induced the uh, by the complex structure J, BJ, J, BJ. So that means that any two such bases must have the same orientation, which completes the proof. Hopefully that all made sense, because this is an important result. The fact that all of the bases have the same orientation is going to be crucial, because on any almost complex manifold that has an integrable complex structure, there's going to be this holomorphic transition, which is going to make sure that all of this stuff is going to work. And so if we have an induced orientation on each of these tangent spaces, then we can merge them into this smooth tensor field, and that is going to be what's going to be our orientation on the entire manifold. Okay, so we're about ready to talk about orientations on the manifold. Okay, so I can never get these things centered for some reason. Right. So an orientation on a manifold, an orientation on a manifold is a nowhere vanishing smooth assignment of top degree exterior forms on the manifold. So essentially what we just said, we're just formalizing that idea. So uh, on each of these tangent spaces, we're going to be assigning an exterior form. It's not allowed to be 0 on any of the tangent spaces. If that's true, then we have something called an orientation. It's defined, this is similar to the definition on the exterior form. It's defined up to a factor of a strictly positive function. So like a function that's positive everywhere on the manifold. The reason we need it to be smooth is, well, smoothness helps, but more importantly, we need it to uh, definitely not be discontinuous, which is what's going to prevent orientations from flipping in the middle of the manifold. Like let's say that we have this manifold here, right? Um, the my favorite manifold, a little uh, square on the ground. So let's say that we had like a positive orientation all on this side, right? And then suddenly it drops off a cliff and then it becomes negative on this side, right? This assignment would not be a consistent orientation, not a consistent orientation. So it definitely can't be discontinuous. So, but we like the smoothness. I'm not sure if there's an extra reason for it, but it makes it easier to work with it on a differentiable manifold. But smoothness definitely means it has to be continuous, and since it has to be the same up to a positive function, the orientation will be positive, will be the same everywhere, right? Um, So that's the idea here. This is a consistent assignment. There's also this idea of an orientable atlas. Orientable atlas. So, and you can think of an so this is what makes something, if you have this, then this is called an orientable manifold. You might have heard of Mobius strips being non-orientable manifolds, and that's because you can't define this nowhere vanishing top degree exterior form, or overall like a non-vanishing differential form. So this would be a uh, differential form, right? So far we've been dealing with exterior forms. Now we're taking a section off of the exterior bundle. So now we have a differential form. And so the other way to think about orientable manifolds is that they have an orientable atlas. So let's say that we have an atlas A, and let's say that we have two local charts on it, U alpha and phi alpha. U alpha, phi alpha, and U beta, phi beta. So what an orientable atlas is that if we have these local coordinates on these, so let's say that these are zj and these are wk. So then we know that we're going to have this transition function, right? Zj of wk, or vice versa. And so the determinant of the coordinate transformation, so partial wk, partial zj, this is the Jacobian, the determinant of the Jacobian. I'm not going to define a Jacobian here. I don't think it's necessary. It's part of multivariable calculus. So I'm going to assume that people know what a Jacobian is. So this is the determinant of the Jacobian. It's bound if this is always greater than 0 for any pair of local coordinates, then A is an orientable, or yes, an orientable atlas. So the other way you can think about an orientable manifold is that it admits an orientable atlas. And we're going to need an orientable atlas in order to define integration on the manifold. So that's how all of this comes together. That's why we are looking at orientations and so forth. Because integration is going to become important when we derive some of the future results. Okay, so almost complex manifolds. Sorry, I think I misspoke when I said that almost complex manifolds need a integrable J. They don't. They all they need is a smooth assignment of J's, right? If they have a smooth assignment of J's, then they have a smooth assignment of volume forms. So uh, almost complex manifolds. So this is a corollary of the theorem that we just proved. Not this. This is the definition. The theorem that we just proved that all real vector spaces with bases induced by J have the same orientation. So corollary to that theorem is that almost complex manifolds are always orientable because they have J twiddle, which is a 1-1 tensor field that is a smooth assignment of J's, JPs, let's say, on each TPM. And from there you get a definition for the standard volume or the induced volume form on that vector space. And so, yeah, like you'd get some EJ, J, EJ, and then just like in our proof, we would construct a volume form from this, EJ, wedge, J, EJ, big wedge, right? So that would be our volume form. And we've shown that all of these volume forms have the same orientation. So because there's a consistent there's a consistent and smooth assignment of orientations, therefore almost complex manifolds are always orientable. Okay. There's actually an even stronger condition when J twiddle is actually integrable. J twiddle actually integrable. So in this case, we have a canonical orientation. It's canonical because it's been induced by, remember we had from lecture 5, a canonical almost complex structure. Almost complex structure. So now this is our next theorem that we're going to prove. Every complex manifold has a canonical orientation. Right? So let's prove this. So the statement of this theorem is that for a complex manifold M, so M is a complex M manifold, we'll have holomorph. Let's say we have a local chart U alpha phi alpha. Then we'll have local coordinates zk, k equals 1 to m, such that zk can be decomposed into two real coordinates, xk plus I yk. So this will have a canonical orientation, canonical orientation induced by these holomorphic coordinates. So canonical orientation. Remember, these holomorphic coordinates we only have because we have a complex manifold. So omega is equal to dx1 wedge dot 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 wedge dxm. This is our top degree form. So, and it doesn't vanish anywhere. Nowhere vanishing. So, what we're going to need to do is we're going to need to show in our proof that this choice of orientation is consistent. So let's do that. We already know that it's going to be a valid choice in the sense that since we're using a canonical almost complex structure and that's a tensor field, it's already a smooth assignment, so we don't have to worry about that part. What we have to worry about is whether or not the orientation will be consistent between coordinate systems. So that's what we're going to check. Let's say that A is this coordinate system that we already have. Let's call it ZJ. In fact, let me call this ZJ as well. ZJ, ZJ, XJ, YJ. So ZJ is equal to XJ plus I YJ. And then we have a different coordinate system, WK. WK is equal to UK plus VK, right? So these are our two local coordinates, and they're by definition decomposable. These are both holomorphic coordinates. Holomorphic coordinates. So we need to know, so in order to show that they have the same orientation, we need to solve for this equation, right? dx1 wedge dot 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 wedge dx, so we're decomposing it into the real sphere, right? So dy1 wedge dot 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 dx m wedge dy m. I just noticed I wrote this wrong. Well, I wrote it in a misleading way. So this should be dx1 wedge dy1 wedge dot 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 wedge. I forgot the dy's here. Okay, so let me explain what happened. So when we decompose this, we wanted to write it as a real differential form. So that's what I did over here. So we're decomposing it into a real differential form. So we have to show, coming back to this equation, so we have to show that, or we know that this will be equal to the determinant of the Jacobian, the real Jacobian, I'm going to call it Jacobian real, in the basis B du1 wedge dv1 wedge dot 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 wedge dum wedge dvm, right? So this is the coordinate transformation we'll need to multiply it by the determinant of the coordinate transformation between the uv coordinates and the xy coordinates. So we need to show that this is a positive number, a positive real number, positive r, right? So, or some people call this an element of r plus. That's what we need to show. So in that case, we will know that between these two arbitrary coordinate systems that we chose, the orientation is preserved, and so therefore for any pair, this orientation will be preserved, and that will complete the proof. Okay, so we're thinking of M as a 2M dimensional real manifold, right? And so we're thinking of these guys, phi. I'm gonna call it phi AB. We don't usually use this notation, but you can kind of understand what I'm going for here. I'm talking about these coordinates and these coordinates. So this is the transition map. We know that this is equal to zk as a function of wj. Did I get that wrong? Yeah. Sorry. It was, this is a typo in my notes. So zj as a function of wk. That's what I meant to write. Anyway, not a big deal. So the Cauchy-Riemann equation. So these are a function of these coordinates, right? So we know that the Cauchy-Riemann equations apply to these. So partial xj partial uk is equal to partial partial yj partial vk. And the other one, partial xj partial vk, is equal to the negative of partial yj partial uk. Right? So these are the Cauchy-Riemann equations. You just have to think of zj as a function of wk, and then you'll get this. These are exactly this is no funny business, just the original Cauchy-Riemann equations. Okay, so then we can write the real Jacobian as, in the basis B, as a block matrix A, B, C, D. Each of these are blocks. Each of these are submatrices. So here A will be equal to, so there's an ordered basis here, right? So we're thinking of the basis as being x1 dot 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 xm y1 dot 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 ym. This makes our argument easier to do, but obviously we're showing that it's any two matrices, but we're ordering the, when we're turning a complex basis into a real basis, we're ordering the real basis like this. So that's what's going to inform the order in which I write these block matrices. If they were mixed, this would be a much more difficult argument to make. So partial xj, partial uk, but of course you could make that argument. That's why the whole proof works. I mean, it has to be independent of coordinate systems, right? But we're using a simpler reference coordinate system to start off from. I'm just copying these off of my notes so that I don't make any mistakes. Partial vk, then you have, so these are entire matrices. So maybe let me reinforce that by using square brackets. So these are, I'm using this notation to draw an element of it, but you can think of this as usual as a matrix where each of these are the elements, right? This is an entire array of all of these partial derivatives. That's what, I mean, you know what a Jacobian is. I don't need to explain it that much. Okay, so two more. Partial uk. We're running out of space, so I'll put this one above. D is equal to partial yj partial vk. And that's the whole Jacobian. So notice that because of the Cauchy-Riemann equations, some of these are the same. So one thing is, let me choose a nice color here. So A is equal to D, and yeah, because of this equation, A is equal to D. Let me put that in the same color. And B is equal to minus C. Let me put a little minus there to remind us. So there we go. So A is equal to D, and B is equal to minus C. So what does that give us? Let us see what happens. So because of that, we get this JR in the B basis is equal to A, B, minus b, a, right? We replaced d with a, and we replaced c with minus b. So this is a very famous form of a matrix, and so this is actually a skew symmetric or anti-symmetric. The skew symmetric is just another way of saying anti-symmetric. Skew symmetric block matrix. Because if you flip it along this diagonal, you see that you get the negative of what you used to get. So there's an important result for this kind of matrix, which I'll shortly explain. It's a bit of a calculation. So let's start with that. So let's say that I'm trying to, we're basically going to start diagonalizing this matrix. So let's say we have a, b, minus b, a, and you would need to do the computation in order to figure this out. Obviously, I already know the answer, so I'm just going to write it out. So let's say that these are all block matrices, remember. So this is the identity matrix. So keep in mind, this is the m by m identity matrix. So let me maybe put a little m here. So I1 m, and then there's a minus sign here. 1 m, and then 1m. If you're, what we're doing here is we're trying to find the symmetry transformation, or sorry, we're trying to find the similarity transformation. Sorry, I forgot the word for it. Yeah. So what this will do is it will transform our matrix into this format. So very simple format, and then we need another matrix here. So this is gonna be minus I by 2 identity matrix, half identity matrix, plus I by 2 identity matrix, and then half identity matrix. So this is the diagonalization. So this has the form, this is essentially a similarity transformation. So if we call this S, we'll call it the D basis. So then this is then S dagger. This is the Hermitian conjugate. And this is J R in the diagonalized basis, whereas this is J R in the B basis. So the way that you calculate determinants for block matrices, if you aren't familiar already, is that you calculate the determinant for these matrices, these submatrices, and then you apply the usual AD minus BC. So we know that the determinant for the identity matrix is 1, so this one will be I, and similarly, so if we want to calculate the determinant of both sides, so det J R B, then this will be equal to determinant of S in the D matrix, in the D basis, multiplied by JR D multiplied by SD dagger. And so we know that determinant of ABC, where ABC are 3 matrices, is equal to determinant of A times determinant of B times determinant of C. So let's use that. So the determinant of this whole matrix, you can calculate it, is 2i multiplied by the determinant of this matrix in the middle, JR D, multiplied by the determinant of this concrete matrix is 1 over 2i. So then these two cancel out. So the determinants are the same, which is usually what you get by diagonalizing a matrix, right? So their determinants stay the same. So, but we know that the determinant of this matrix is going to be AD minus BC, which is exactly determinant of a minus ib times a plus ib, which is equal to determinant of mod a minus ib squared, which is equal to determinant of, which is equal to the modulus of the determinant of a minus ib whole squared, which is greater than or equal to 0, right? So we need to make sure that this isn't equal to 0. So let's see. So we're going to be able to do an interesting thing. Let's think about what JR in the diagonalized basis gives us. So let's look at a minus ib. Let's look at the jkth element of it. Let me see. J is on the top, k is on the bottom. So this is equal to, remember from our A, B, C, D definitions, so this is going to be partial xj, partial uk, and then we get a minus I, partial xj, partial vk. So then this is equal to partial uk plus I plus 1 over I partial vk of partial xj. Let me check my notes to make sure I'm not making a mistake here. So this is equal to, this is actually something called the Wirtinger derivative. It's actually 2 times the Wirtinger derivative. So this is equal to partial wk. This is equal to 2 times partial wk. So this is equal to yeah, in fact, let's try to break this down in a slightly different way. Let's say that this is equal to half partial xj partial uk plus 1 over I partial xj partial vk plus half partial yj. So we're using the CR equations here. Partial vk. We need an I out in front so that works out. Plus, does it? Okay, let's not do that first of all. So let's just say this, and then we're gonna get a minus sign over here, minus 1 over I partial y j partial uk, and we're going to need to take an I out of these. So then we get I over 2, and then we swap the places of these, right? So so then we get partial yj partial uk minus 1 over, or plus 1 over I partial yj partial vk. And this together gives us half. Let's take the operator out. Partial uk plus 1 over I partial vk of xj plus I yj. So let's recap, because I just did a really complicated thing here. I divided this into two pieces that look the same, uh, two terms, right? They would be identical, but I applied the Cauchy-Riemann equations to this. After I applied the Cauchy-Riemann equations, I factored out one factor of I, which swapped the two terms. So the u term was supposed to be here and the v term was supposed to be here, but then when I factored out the I, it swapped those and it added an extra 1 over I on one of them. So that's how we got that. That also gives us this nice I that's over here, because then this becomes Zj, and this becomes 1. So this is the Wertinger derivative. So this is 1 over, or sorry, not 1 over, but partial Wk, which is exactly what we want. We want partial Zj, partial Wk. If you look at A plus IB, then that will give you partial Z bar J, partial W bar K. And the idea is that this thing is essentially, and therefore the thing that's inside this, the thing that's inside here is essentially JC. This is the complex Jacobian, which is equal to this block matrix, partial Zj, partial Wk. Because we're on a holomorphic coordinate, these are all 0, partial Z bar J, partial W bar K. Right? So, and that's exactly what we got, because this is now partial Zj, partial Wk, and this is partial Z bar J, partial W bar K. So this is essentially the determinant of JC. So this is the determinant of JC squared, but because we're on a holomorphic atlas, so here we're invoking our complex structure on our complex manifold, holomorphic atlas. This has to be greater than 0. This cannot be degenerate. Remember, we were saying before that this cannot be degenerate. So on a complex manifold. So this is the thing that will save us from having this be an equality. So now we know that this is not greater than or equal to 0. It's strictly greater than 0. So therefore, we know that this is greater than 0. And that completes the proof, right? Because remember, if we go back to the part where we were saying that, so now we know that this is definitely positive, which means that these two local coordinates have the same orientation, right? So therefore, because these two coordinates that we chose were arbitrary, so therefore any two local coordinates over the same portion, obviously, have the same orientation. And so that means that we have a consistent definition. It's well defined. Consistent definition, as required by our definition of orientation on the manifold. So therefore, we've proven this claim that we have a canonical orientation given by this form. All right, so that proves, let's go back, that proves our claim. We'll need to go to the next page now. So a corollary of this fact is that holomorphic, so complex manifolds are naturally are canonically oriented, right? And so that translates to the fact that they have an oriented atlas, well, how do I want to say this? That translates to the fact that they have a canonical oriented atlas. Oriented, I'm going to underline that, oriented atlas. And that's the atlas on the manifold. It's that holomorphic atlas. Holomorphic atlas. The other way you can think about this is that holomorphic atlases are always oriented, because we know that det JC squared is greater than 0. So that's the idea here. Okay, before we get to integrations, I just want to show the standard complex volume form. So we looked at the standard real volume form, right? So the standard complex volume form is equal to omega is equal to I over 2 to the power m. That's that factor that we saw before again. And then dz 1 wedge dot 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 dz m wedge dz okay, let's write it like this: dz bar 1 wedge dot 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 wedge dz 1 or dz m wedge dz bar m. This is the complex standard volume form, or that doesn't sound right. Standard complex volume form. And it's a real valued form. That sounds kind of counterintuitive. It's a real valued form because even though it uses complex numbers and complex values, in fact, if you did the computation, omega bar, the complex conjugate of omega, is actually equal to omega. So it's technically in the elements, using elements of the complex space, but it's in the subspace of the complex space, which is real. So it's a real top degree form. This is going to be important. Also, important thing to note, this is not, I don't know if this might be necessary for some people to avoid confusion. I'm going to put that in a box because this is important. But this is not the Kähler form. I don't know if anyone was going to mistake this for the Kähler form, but I've been talking about the Kähler form over and over again, and I just introduced this form. So this is not the Kähler form. The Kähler form is not a top degree form at all. Just make sure, like, we're not alluding to the fact that, oh, secretly this is the Kähler form. The Kähler form is different. We're going to talk about it later on when we introduce the Hermitian manifolds and stuff. So this is just the standard complex volume form. All right. It's related. The Kähler form is related to the standard complex volume form, but we'll get more into that when we talk about the Kähler form. Okay, good. So now we talk about integration. Integration, because we have all of the building blocks now in place. We know what an orientation on a manifold is. We know that a complex manifold is canonically orientable. So integration on complex manifolds is kind of simpler to define because of that canonical orientation. And remember, why did we need orientation for integration? Because let's say that you have an integral in one of the, let's say you're integrating over some manifold M of some of some differential form. Well, it doesn't need to be a exterior derivative. So some differential form. Let's say that this whole thing, I'm just going to use a little bit of like abusive notation here. Let's say that this is in some, you're expressing this in some basis B. Let's say that you take it to another basis. Let's do that in a different color. Let's take it to a different basis. Let's call this one A. I don't know, there's no reason why we couldn't call this one A. And let's call this one B. Then we want that, again, like, coordinates are not real, right? I keep talking about this idea, coordinates are not real. So in this basis, the the value shouldn't be the value that you get from the integration should be a geometrical property of the manifold, right? So the value shouldn't depend on the fact that we change the bases. But if we change the orientation of the integral, the of the manifold, then the integral would could change sign based on what orientation the basis was, and nothing else would have changed. Okay, so now that we know what an orientation is, why an orientation is, uh, what an orientation is, why an orientation is always induced on a complex manifold, and that orientations are needed for integration. So now let's start to define what an integration on a manifold actually is. So at the oh, we're just about to define integrations. It's very exciting, very cool. Problem is that we still have the problem that we have multiple local charts. Every time we define anything, the problem is always we have coordinates, and the coordinates need to agree with each other, right? So the problem here is slightly different. It's that, let's say that we have this subpatch of our manifold that we're looking from the top, right? Let's say that this is U alpha, and let's say that we're looking at a specific point P in the middle. So there could be multiple local patches that overlap this region, right? Let's say that this one is U alpha, this one is U beta. Let's say that this one is U gamma and U delta. So we're going to have a contribution from each of the local charts. And so how do we pick which presentation of P is going to be the true one, right? And our answer is going to be that we're not going to choose any of them. We're just going to make sure that whatever choice that we make, it doesn't actually matter. So what we're going to do is we're going to use something called a partition of unity, which is a very, very fancy word. Partition of unity, which is just a way of cutting up. Let's say that this thing is the whole thing, right? This is 1, so cutting up the number 1. That's a very hard to understand number 1. So we're partitioning it. We're just cutting it into pieces. So what we're going to do is we're going to weight this the contribution of P from each of the value of the integral from each of these local charts, so that the total weight always equals to 1. So no matter how you chose your charts, if the value always equals to 1, then the overall contribution at that point will, or maybe like in a little local neighborhood around that point, whatever you want to think about it as, so that will always be the same, so that we can get a consistent answer for the integral. We basically everything that we're doing so far is to make the integral a consistent definition. So, right, let's say that U beta is going to contribute this fraction, and then U gamma is going to contribute this fraction, and U delta is going to contribute this fraction. But we need to make sure that the contributions add up, or like the weight of the contributions add up to 1, so that this is consistent. So let's define a partition of unity. Partition of unity. If you did a lot of probability before, these like partitions of unity or weighting is like a concept that you might be familiar with already. So let's say that M is a smooth manifold. Then let's say that U alpha is an open cover, and we know that this exists because we have the charts on the manifold. Open cover on M, open cover of M. And so a partition, we call it a partition of unity subordinate very fancy terminology, subordinate to U alpha, the cover. So what is it? It's a set of maps, is a set of maps, one map for each U alpha, set of maps, rho alpha that takes you from M to the closed interval 0 to 1. And so this is going to be the weight, right? This is the weight. And this is the point for which we are assigning the weight. Subject to a few conditions, so we're going to need a little bit of real analysis here. Supremum of rho alpha, which is the point that creates the highest value of rho alpha, which has to be a subset of sorry, not M, of U alpha for all alpha, right? 2, we also require that the collection supremum of rho alpha for all alpha, element of that index set for U alpha is a locally finite set. Locally finite set. That's the rigorous way of saying that we want a finite number of suprema for any local neighborhood. 3. And this is the weighting condition. So weighting as in WEIGHT, as we were talking about. So rho alpha of P, the total weight on a single point has to equal 1 for all P element of M. So this is the weighting condition. Let me write that out. Weighting condition. This ensures that the contribution from each point is normalized, right? The normalization being that the total weight is equal to 1. Okay, so now that we have a partition of unity, and we've already talked about orientable charts, right? So now we can define an integration on, so definition, integration on the manifold, big result or big definition of this episode. So let M be an oriented M manifold. M manifold is just short for M-dimensional manifold. And omega is okay, so let's not even call it omega because that's going to confuse us with the volume form. Let's just call it alpha. And let's say that alpha is an element of omega n m. So it's a top degree form. Sorry, omega m m. So this is a top degree form. Top degree form. So top degree again just means that if the dimension of the manifold is m, then it's an m degree form. So that's basically what top degree form means, just to remind everyone. And on compact support. Compact support. Compact support means it's a term from topology, which means that alpha has to be non-zero on a finite subset of the manifold, or compact subset of the manifold. Okay. So let U alpha phi alpha be a chart. Let the set U alpha phi alpha be a choice of oriented atlas. So here's where oriented atlases are coming in. Oriented atlas on M and there's a lot of things that we're going to need to let exist. So let rho alpha, a set rho alpha, be a partition of unity, I'm not going to write that whole thing, subordinate to u alpha. Okay, so now we're ready. This is, again, like, so now that so here you can see that we needed that partition of unity. So everything we've covered so far, oriented M manifold, so the fact that a complex manifold will always be this, that's also something that we needed to show, complex M manifold. So we really couldn't have defined this any sooner than what we did. That's what I'm trying to get at. So then in local coordinates, alpha is equal to f yeah, we shouldn't call it alpha because we already have an index alpha. Let me rewrite that. So that's beta. That should fix everything. So beta is equal to f alpha of x dx1 wedge dot 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 wedge dx m. So remember, this idea of integration, we said here complex M manifold, right? This doesn't have to be a complex M manifold. This is also definable on the reals. And the way we're defining it on the complex space is by defining or is by thinking of the complex space as a 2M dimensional real space. So these are all real. That's why I wrote X's over here. And when you translate the Z's, you translate them as Z is equal to X plus IY, and that's where you get all of these coordinates from. So then the integral, finally, integral M of beta is equal to the sum over beta. We couldn't write this sum unless we had a finite, finite or a countably infinite number of sets in this cover, right? That's what this is being afforded to us by the paracompactness of our manifold, if you think back to lecture 1. So then this is the integral over phi alpha of u alpha, which is the coordinate chart of u alpha. So u alpha is the actual set on the manifold, right? And phi alpha of u alpha is our map of the manifold. So just to give a refresher, we did talk about that a while ago. So let me just write this out, and then we can talk about what this means. So phi alpha inverse d dnx. This is the Lebesgue measure. Lebesgue measure. We're not going to get into measure theory. So this is what it means to integrate a differential form. So what are we doing here? Let's think about this integrand. First of all, okay, so phi alpha takes us from the chart to the manifold, and then after we have, this should be a bit bigger of a circle here. So after we have that, we get f alpha, which is the coefficient. So this is the actual value that we're trying to add, right? Where we're trying to add the value of f alpha at the point that we're considering. So then once we have that, we weighted, this is the weight of the value of f alpha in the alpha chart. So, and then we're summing it over. Why did I write beta here? That should be alpha. I'm getting myself confused. So this is a sum over alpha of all of these charts, and then we weight each of the contributions being this, the value of this at that point, weighted by its weight at that point. So that's what we're doing here. That's what this integrand means. Integrand is a weighted sum. Weighted sum. So that is the integration on a manifold. We now have just a few things left to do. One thing is that we so far have defined k-forms, right? So before we conclude on integrations, the reason uh, why this is well defined is for a few things. We don't have enough time to get into it fully, but let me just write it out. So we need to know that this is coordinate independent, and the reason why we know it's coordinate independent is because of three reasons. It's independent of the partition of unity of the chosen partition of unity, and that's because we said that for any choice of chart, as we talked about when we talked about the partitions of unity, is that for any choice of atlas, the partition of unity has to add up to 1, has to add up to 1. So this is actually, you can prove that this actually makes it so that the specific choice of partition of unity doesn't matter as long as this is true. So this is just a justification. This is not a proof. So secondly, it's atlas independent. Atlas independent. It's atlas independent because of what we said with overlapping charts having a positive determinant. That goes back to the proof that we did that every real space has the same orientation. So positive Jacobian determinant. And then 3, we avoid convergence issues. So convergence is always a problem, right, with integrals. So we avoid convergence issues by having that part on the compact support. That's why that exists, is because compact support. The compact support means that unless we have an infinite value anywhere in the support subspace, there's no way that we could get an infinite or like a asymptotical value, right? So if everything is finite inside that compact support, we can't get an infinity by adding too many numbers together. So that's how we deal with that. So next, I would just like to say, how do we integrate PQ forms? Because PQ forms are very, very important. Well, the thing is that, so the integral of alpha over some manifold M is equal to, is not equal to 0 as long as P plus Q is equal to, so let's say that this is an M manifold, right? M manifold. That means that this has to equal M, but if this actually is a complex bigrade, then we know that the holomorphic space, the holomorphic subspace, can only go up to M, and this has to equal 2M, and the anti-holomorphic space, can also go up to M. So the only combination is P is equal to M, Q is equal to M. So therefore, the only integrable PQ forms that according to our definition are MM forms. In other words, they are top degree forms. Well, they have to, okay, so they have to be top degree forms, but the only top degree forms available are MM forms. That's what we're saying. And remember, our like, notice that our complex standard complex volume form was a top degree form of this this variety volume form, right? So that is the how you integrate PQ forms, or like if there are any restrictions. It's just that the only kind of PQ forms that you can integrate are MM forms on an M manifold. Okay. Last, there's one last result that we want to show, or we want to like state because it's going to be really important for the rest of the course. That is a theorem. We're not going to prove it here. Stokes theorem. Stokes theorem, you might have become familiar with it because of multivariable calculus, but fundamentally Stokes theorem is a differential geometric result, at least I believe so, because it's something called the generalized Stokes theorem. And some people call this the generalized Stokes theorem because they think of the Stokes theorem as the particular result for 3 dimensions, is written in terms of differential forms. So what Stokes theorem tells you is that the flow on the boundary or let's say the sum of the flow, the sum of the net flow. I'm trying to workshop this right here. The net flow on the boundary is equal to the sum of the flow on the interior. That's like a vague and intuitive way of thinking about it. So what does that mean? So basically what it's saying is that let's say that you have this manifold with a boundary. So this is called the interior. It's an open set. And this is called the boundary. And so what it's saying is that if you have a form on the boundary, let's call it omega, because we love calling forms omega. So you can add up the form on the boundary by integrating it on the boundary manifold. And that will give you the same thing as if you added up all the contributions of d omega on the interior. So that is the result. Integral of m of d omega is equal to the integral on the boundary of m of omega. This is Stokes' theorem. So what is the boundary? Let's talk about boundaries right now. So what is a manifold with a boundary? Okay, so a manifold with a boundary is manifold with boundary. So far our manifolds couldn't have had boundaries, right? Because they had to be topologically identical or homeomorphic, let's say, to Rn or Cn, right? And that precludes there being a boundary because Rn and Cn don't have boundaries to them. So what do we say here? So we go from being locally homeomorphic to Rn or Cm to locally homeomorphic to Rn or Cm or H, this space called Hn. This is called half space or upper half space. Upper half space. It's literally the upper half of the coordinate plane. That's all it is. I just wrote upper half half. I'm getting tired. Upper half space. So basically the idea is that this part, if we take a local patch here, this is isomorphic to Rn or Cm, right? But if we take a little patch here, or let's say here, then it will look like this. It will be isomorphic, or homeomorphic, I should say, to this kind of space, where only the upper half is part of the space, right? And this part is not part of the space. That's what this little patch looks like. So that's how we get the boundary. And if your point, right, let's say that I have a point P on the boundary. How do we know that it's on the boundary? The way we know that some point is on the boundary is if all neighborhoods, no matter how small, neighborhoods, let me shorten that, neighborhoods of P in the are homeomorphic to Hn. That's how we know whether the point on the manifold is going to be an interior point or a boundary point. If it's a boundary point, if like let's say that like what I'm trying to say here is that if I took a point here, right, and I took let's say that that's Q, and I took a local neighborhood like that, this neighborhood would look like the upper half space, right? Because it contains part of the boundary. But that doesn't count, because what I'm saying is that there's an even smaller neighborhood that doesn't look like this looks like Rn or Cm, depending on the manifold, right? So this is then not a boundary. This is not a boundary. This is an interior point. Okay? But on a boundary, no matter how small of a neighborhood you take, you'll have to exit the manifold, right? And therefore you will look like upper half space. So no matter how small you go, that will look like upper half space. That's what a manifold with a boundary looks like. Okay. So because we need to integrate on the boundary, so the boundary itself is a submanifold. The boundary is a submanifold, and therefore, so it's a subspace that's also a manifold, and it is we need to integrate on it to define Stokes' theorem, right? So it also has to be oriented. It has to be an oriented submanifold. And what we can claim is that, or what we're claiming is that there's an induced orientation on the boundary. Induced orientation on the boundary. Right? Proposition. And so let's see how this works. So so the boundary is this symbol, which we call del m. So let's say that P is an element of del m. In that case, we choose a basis, because we need a basis in order to choose an orientation. So choose some basis v1 dot 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 vn minus 1. So right, I forgot to mention this is an m minus 1 dimensional submanifold. If m is m dimensional, then this is an m minus 1 dimensional submanifold. So this will be vm minus 1, right? So then this is called positive orientation. So this is how we're inducing the orientation on the boundary, right? So it's called a positive orientation if n v1 dot 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 Vm minus 1 is a positive orientation on M. What's N? We just define this strange letter N, or so this is called the outward pointing vector. What is the outward pointing vector? The outward pointing vector is defined like this. So let's define a curve. Gamma goes from minus epsilon 0 to m. This is a parametric curve. Remember from lecture 1 we were defining these. This is it should be intuitive that we're starting by defining a parametric curve, because that's how we define tangent vectors in the first place. So gamma of 0 is equal to p. That's pretty standard for us. So basically, let's graph this. So this is the boundary, right? This is the interior of the manifold. Let's say that we have a curve that goes like this, right? That's the endpoint of the curve. That's p over there. So this is where gamma is equal to 0. Gamma of 0 is equal to p. So we want to define the derivative at this point, right? The way we define the derivative is we say that gamma, sorry, I should do this also in orange, gamma prime of 0 is equal to, this is, well, this is by definition this outward pointing vector n, right? And the way we define this is that we take this little extension minus epsilon plus delta, where so this plus delta is called a smooth, this is going to be called a smooth extension. We don't have that much time to get into what a smooth extension is, but I think you can understand that, like, we just extend this so that extend this curve smoothly in order to completely define this. You could also think of it instead of being a smooth extension as a one-sided limit, one-sided limit. So that could also inform you how to. So the smooth extension is basically there's a unique extension of this curve that will take us from that will allow us to define a derivative, right? If it were any other curve, it would bend slightly, and therefore there would be no possible derivative to define over there. So we make this smooth extension, and that's how we define gamma prime of 0. And so I've already alluded to it this here, but every other value of gamma is going to be negative, right? So for all t is less than 0, gamma of t is an element of m. Gamma of t is an element of m minus the boundary, so it's on the interior. We don't have a fancy name for that, so we're just going to call it m. Set disclusion, set exclusion del m, right? So this is the interior. Right. So that's it. So this is how we induce the orientation on the boundary, which means that, coming back to Stokes' theorem, this is now all defined, right? We have partial m d omega. This is the exterior derivative, and this is equal to the integral of del m omega, right? So this is Stokes' theorem. I kind of wanted to close by talking about Stokes' theorem in particular dimensions. Let's think about Stokes' theorem on R. I think you've already heard of it. Or the generalized Stokes' theorem on R. Let's say that you have a function, right? If we wanted to find the area under a certain part, we would take the integral, right? So let's say that this is A and this is B, and that f is the antiderivative of, so this function is f of x, this is x. So then let's say that the integral, the antiderivative of f of x dx So then the fundamental theorem of calculus says that integral of f of x dx from a to b is equal to the antiderivative at b minus the antiderivative at a. And if you look at Stokes' theorem, this is exactly the same thing. Sorry, this should be a derivative. So this is d omega. This is omega evaluated at the boundary, right? So, and these are the boundary values, right? So this is the boundary. Let me color code that. So this side is the boundary on boundary. So this is the boundary part, and this is the interior. So we're trying to add little areas, and what Stokes' theorem is telling us is that adding the areas, adding the little tiny infinitesimal areas, is the same thing as taking the antiderivative and then subtracting the antiderivative here at b from the antiderivative at a. That's Stokes' theorem. And you might have seen Stokes' theorem in higher dimensions too. There's a particular one that looks like this. Let me pull it up so that I can write it correctly. The double integral, the surface integral, over a surface, we're going to call it del m. That's going to be our surface. The curl of a vector well, yeah, I mean, this is Maxwell's equation, so it's equal to sorry, this should be m. This is m, and this is del m, and then this is an instance of Stokes' theorem as well, right? This is what people call Stokes' theorem. So this is the evaluation on the interior, and this is the evaluation on the boundary. This is what happens when you have a surface, an area, and you have a line integral on the boundary. Let's do it like this. So you can have a line integral on a boundary. So then this is del m, or you can have you can evaluate the sum of the curls on the inside. That is also a manifestation of Stokes' theorem. It's really interesting and very beautiful that you can capture all of these in one equation using differential forms. I believe there's another version that has to do with divergences and the two-dimensional surfaces of those, but I can't pull up the equation right now. But you know, you can look that up. That is also a version of this generalized Stokes theorem. So we're going to need this to integrate PQ forms in, for example, the Hodge decomposition is going to use this. I think we're going to use this in cohomology, and so that's why we needed all of this. So this is Stokes theorem. So that concludes the last big point, which was Stokes theorem. And so let's do a brief recap before we wind down for today. Recap. So what did we look at today? One, we looked at, right, so we wanted to define integrations. That's where we're going to start, even though we did integration second. So we started with integrations. And then we saw that in order for integration to be well defined, we need orientations. Orientations to be well defined, coordinate independent, right? So then we started by saying, okay, let's do this bottom-up construction. We take the vector space, so orientation on the real vector space, um, and then we defined something called a volume form, which was a non-zero top degree form, non-zero top degree form. So yeah, volume form. We use that to define the orientation on the vector space. Then we said that the orientation. Oh, right. Then before we defined orientation on a manifold, we also quickly proved, maybe not so quickly, proved that all orientations or all bases, because orientations are actually a function of the bases, all bases um, induced by J have the same orientation for we defined orientable manifolds by thinking of the differential form that was a section of the orientation form, the bundle of orientation forms. So choice of volume, differential volume form, let's call it, right? So then we saw that almost complex manifolds always have an orientation, always have an orientation. Six, we saw that complex manifolds additionally, because of their holomorphic coordinates, they always have a canonical canonical orientation. So then we looked at the fact that also with orientable manifolds, we looked at orientable atlases, right? So then we got then we went over we defined the standard complex form, standard complex volume form, which is not the color form. And then 8, we defined integration finally, because we now had enough tools to define integration on a manifold, or integration of differential forms on a manifold. And then in order to do that, we define something called a partition of unity. We did that because the partitions of because we have multiple charts on the same point, and we need to know how to consistently assign a number to an integral when we have multiple charts that will assign a number to them. So we used a partition of unity rho alpha such that sum alpha rho alpha of p is equal to 1. That's the normalization that we used. We also so then with the orientable atlases, then we were able to define integration as integral of alpha of m is equal to sum of alpha integral of rho alpha after f alpha after phi of alpha inverse dnx, where this is just a measure. This is not a differential form. It's a measure. Because if we keep it in a form context, we also, like, we're trying to figure out what the integral of a differential form is. If we put the integral inside the definition another differential form, then it becomes circular. We can no longer define it, right? So this can't be a differential form. This has to be just a measure. Okay, so that's kind of the idea there. So this was the last thing, and then lastly we defined a manifold with a boundary, manifold with boundary, plus we defined what a boundary was. We figured out how to induce, or yeah, we figured out what a boundary was, how to induce an orientation on a boundary, an orientation. We skipped over, I do know that we skipped over how exactly we figure out the derivative on the end of the of that curve that we were using to figure out the outward pointing vector. Maybe I'll come back to that in the future, or I'll put it in the notes. Induce an orientation on the boundary. And then we were able to define Stokes' theorem, which is that d omega, integrating d omega on M is the same thing as integrating omega on the boundary of M, which gives us a lot of cool results in standard multivariable calculus when we dualize it to the vector space. And so we get things like the fundamental theorem of calculus, fundamental, you know it's important because it's called the fundamental theorem, right? Fundamental theorem. You can only have one fundamental theorem of calculus. In fact, I think that there are two actually. But fundamental theorem of calculus, we get the curl one. I'm not sure. I think that one's just called Stokes' theorem most of the time. Stokes' theorem. So this one's usually called generalized Stokes' theorem. I think the reason I didn't find that last one is I think it's called Green's theorem. Let me double check that. Green's theorem. We're doing some live research here. Green's theorem. Yes, the 3D version. So the 2D version is called Stokes' theorem, and the 3D version is called Green's theorem. Okay, and we're going to use the generalized version that works on any dimensional manifold. It's just interesting, I think. I really found it interesting when I found out that this works in any dimension, that all of these results are just manifestations of an underlying differential geometric result. And you just have to think about Rn as a manifold, and then you can find that all of these results come out of that framework. And they're just other tools that are translations of things that are in differential geometry. It's one of those things that most attracted me to differential geometry, is this ability to form these more powerful tools that generalize the tools that we already had in multivariable calculus. Okay, so that is it for today's lecture. That's lecture 7. We're done with it. Unfortunately, ever since we started that proof, what was it? Which proof was it? It was the proof that that complex manifolds have canonical orientation. This was an offline recording from that point. So half of this is a live recording and half of this is an offline recording. We unfortunately had an internet disruption during the live class, and so I had to come and record this later, but thankfully now it's recorded. We'll stitch it together, and hopefully that was pretty overall mostly seamless. It's a good viewing experience. So hopefully next time something like that is not going to happen. Hopefully we will have time to do lecture 8, and so I'll see you next time on lecture 8, when next time we will do Dolbeau for real this time. I'm not going to keep you hanging for another few lectures. So next time, for real, we're going to do Dolbeau cohomology group. I'm excited for that one. I don't know, maybe you guys are excited for it too. It's one of my favorite topics to talk about how we detect holes in manifolds using the cohomology process. Okay, so see you next time on Dolbo cohomology group and complex differential geometry.